Now, in the previous exercise, you saw how to actually create the equation of a chord, and a chord is like this situation. What you're going to see now in exercise 9F is how we create the equation of a tangent. That's this one, is a tangent touching at point 2at, at squared, and the normal to that. So this one's the normal. And what do we know about a normal? A normal just has perpendicular gradient to the tangent. So we're going to be investigating the gradient of the tangent. So because the tangent is a straight line, normal is a straight line, how do we get the equations of tangents and straight lines? How do we get the equations of straight lines? It's once we know a point that it passes through, that straight line passes through, then we're interested in the gradient. So we'll be looking for the gradient of the tangent, and then it makes good sense then to investigate the normal to the tangent, because we know that there's a connection between the gradient of the normal and the gradient of the tangent. And again, really the emphasis is going to be on the process. It's not going to be on the actual equation, because the equations are given on your reference sheet. So if we looked at the reference sheet, it would look like this. And the equation of the tangent and the normal's actually there. I'd better just check that. Yeah, I think the reference sheet actually in terms of that hasn't changed. So because they're going to give you these formulas, then you can imagine that a question is going to be more about show that this is the equation. But really it just relies on the things that you already have perfected, like getting gradients, getting equations of lines, etc. The only variation is at the way our point is going to be labelled. So instead of x and y, we're going to use 2at and at squared, or which is actually the format of the questions on the formula sheet. But you've done enough questions now that you can actually see that the parameter could be t, could be p, could be q, could be r, and so that we can distinguish between 2 points. We need a different variable for the parameter because we need to be able to denote two different points. So, like I said before, because if we're finding the equation of a straight line, and we know only one point that it passes through, then we definitely always need to find another piece of information, and you'll find that this gradient, because that's what calculus is all about, isn't it? When you differentiate, you're finding an expression for the gradient along the curve. So the whole process of differentiation focuses on getting the gradient. So, and like I've said, when I introduced calculus, differentiating, that almost every topic you do, there'll be an aspect of calculus in it, even if it's just at this level where you are just using a calculus to find the gradient at a particular point. You can see that, calculus is being used. So we are going to use our calculus to find the gradient, an expression for the gradient. But we have a little problem. Our equation will be written in the form x squared equals 4ay. We know that. To use parametric form, this is the format we need our equation to be in. Now, that's not in a very friendly calculus form to differentiate, because when I differentiate, I want y to be sitting by itself so that I can get dy dx. It's only dy dx that gives me an expression for the gradient. So I'm going to need to do some rearranging of my equation first and get it into a format where I can differentiate it. So that's all I'll be doing. And there's nothing difficult about that. It's just making y the subject, which is again a skill that you've been introduced to for a long time, making one particular variable the subject. Well, it's really the same process as solving, getting a pronumeral by itself. Okay, so let's have a look. We're going to start with x squared is 4ay, and we will need to get it into a format that we can differentiate. Why are we differentiating? We're differentiating so we can get an expression for the gradient. So we could see that y will be equal to x squared, and you'll have to divide by 4a. Now, a is a constant. A is just a number that is depends on the size of the parabola. dy dx, we're going to use bring the power to the front, subtract 1 from the power, and keep our coefficient. That y is equal to, it's just 1 over 4a times x squared. So this is like a coefficient or a number, and differentiating, bring the 2 to the front. So dy dx will be bring 2 to the front, bring the power to the front, 1 over 4a times and subtract 1 from your power. And you can see that the 2 and the 4, and so we get x over 2a. That is our expression for the gradient. Great, we've got an expression for the gradient. If I want to, and I do, I'm going to want to know the gradient at this point here, the gradient at the point 2at squared, then it says the gradient is found by this calculation. My value for x is 2at. I'll write that, but x is 2at. It's the x value. Therefore, the gradient value is 2at over 2a. The gradient is t. The gradient is t. What was t? The parameter. And this is what I was saying, I think last lesson, about the genius of parametric equations, that the mathematician that realized that this basic parabola could have its coordinates written in this format, 2at at squared, such that the gradient at any point was the parameter value, is, like I said, a genius. So the simplicity of this result is they've made it so simple, is why we study the parabola in parametric form. The gradient of a tangent at any point is basically the parameter value. So the equation of the tangent can be found. So this is my x1, y1. We've got m is t. Oh, whoops, did I do that on the next page? Yeah. The gradient of the normal, oh, no, I didn't. That goes on to normal. Is using point gradient, y minus y1 is m times x minus x1. So it's y minus my y1 is at squared. My gradient is my parameter, x minus 2at. Now, is there anything y minus 80? Any common factors? Any common terms I'm looking for? Minus 2at squared. And what's the connection between that and the way it's written on the sheet? Let me just go back. So they've got it that the tangent is y is equal to tx minus at squared. So I've got a little bit more work to do on mine. Y is equal to, well, there's the tx. Minus 2 of these, bring this one over. It'll become a plus, which means there'll only be minus 1 of those. Oh, there wasn't that much more to do to get it in the format that's on the formula sheet. And now with the normal, we know the gradient of the normal, because the normal is perpendicular, it'll be minus 1 on t. And to get the equation of the normal, we're going to use, because a normal is just a straight line, y minus y1, m times x minus x1, point gradient. Same point, now the gradient's this. You can see I've subbed that in the place of the gradient. I've multiplied both sides by t, so you get your yt minus at cubed. And so I'm just multiplying this bracket by a negative 1, so it's negative x, but it's plus 2at. And the format on the reference sheet is just they've decided to bring the x over and make it positive, put it with the yt term, take the at cubed to the right hand side, make it a positive and sit it here with the 2at. So see how you go with exercise 9F, questions 1 to 5.